The recent confirmation of advanced flight testing for China's GJX program represents a watershed moment in aerospace development, marking the transition from a technological demonstrator to a validated weapons system approaching operational capability. This successful testing phase, conducted under rigorous conditions at dedicated flight test centers, has yielded petabytes of performance data that validate years of computational modeling and subscale testing. The aircraft's performance during these evaluations has demonstrated not only basic airworthiness but exceptional stability in the demanding flight regimes required for penetration of sophisticated air defense networks. The collected data spans structural response to high-G maneuvers, thermal management during sustained high-speed flight, and the effectiveness of signature reduction technologies across the electromagnetic spectrum. The technological achievements embodied in the GJX extend beyond its visible airframe to deeply integrated systems that represent generational advances in multiple domains. The vehicle's core structure utilizes third-generation composite materials with customized polymer matrices that provide both structural strength and tailored radar-absorbent properties at the molecular level. This material science advancement allows for the creation of large, load-bearing structures that inherently absorb radar energy rather than merely deflecting it, while maintaining thermal stability across the extreme temperature variations encountered during high-altitude flight and atmospheric re-entry from cruise altitudes. The manufacturing processes developed specifically for this program involve automated fiber placement systems capable of creating complex curved surfaces with microscopic precision, ensuring perfect continuity across all structural joints where radar reflections might otherwise occur. The propulsion system integration represents another landmark achievement, with the engine installation functioning as a fully integrated thermodynamic system rather than merely a power source. The air intake configuration employs boundary layer ingestion technology that manages the slow-moving air adjacent to the fuselage, improving efficiency while contributing to thermal management. The engines themselves feature advanced ceramic matrix composite components in the hot section, allowing higher operating temperatures for improved efficiency while reducing infrared signature. The exhaust system incorporates a multi-stage cooling process that mixes engine core flow with bypass air and additional cooling channels embedded within the airframe structure itself, achieving temperature reductions that place the thermal signature below the detection threshold of current-generation infrared surveillance systems. Within the avionics architecture, the GJX employs a distributed computing system that segregates functions across multiple redundant computing modules connected by fiber optic data networks capable of terabit per second data transfer. This system architecture enables real-time sensor fusion from multiple active and passive sensors, combining data from the active electronically scanned array radar, electronic support measures system, electro-optical infrared targeting system, and communications intelligence sensors into a single integrated tactical picture. The computing system employs artificial intelligence algorithms trained on massive datasets of simulated engagements, enabling pattern recognition of threats and targets orders of magnitude faster than human operators could achieve. This system continuously monitors the electromagnetic environment, updating the aircraft's threat model and automatically adjusting flight path and defensive systems to optimize survivability. The payload system represents a paradigm shift in unmanned weapons carriage, with the internal weapons bay designed as a modular system that can be reconfigured in hours rather than days. The bay incorporates a standardized interface that provides power, cooling, data, and mechanical attachment points for various mission packages. These include not only conventional precision-guided munitions but also specialized payloads such as electronic attack systems that can be deployed to create localized denial areas, reconnaissance drones for extending the sensor footprint, or directed energy weapons currently in development. The bay design includes an advanced launch system that can accommodate weapons of varying sizes and configurations, using electromagnetic ejection rather than pyrotechnics to reduce signature and provide more precise control over separation dynamics. The program's development roadmap extends through at least 3 major capability blocks over the coming decade. The initial operational capability configuration focuses on the core missions of intelligence, surveillance, and reconnaissance paired with precision strike using existing weapons. The second block, already in advanced development, introduces significantly enhanced sensors including a quantum radar technology demonstrator that could potentially detect stealth aircraft, and hyperspectral imaging systems capable of identifying targets through camouflage or foliage. This block will also integrate next-generation munitions specifically designed for internal carriage in stealth aircraft, including hypersonic cruise missiles and multi-mode seekers that are resistant to electronic countermeasures. The third capability block, currently in conceptual design, envisions a fundamentally different operational paradigm centered on collaborative autonomy. This would enable groups of GJX aircraft to operate as a networked system, sharing processing tasks, sensor coverage, and offensive-defensive capabilities across the group. Individual aircraft would specialize roles within the group, with some focusing on sensor coverage while others maintain weapons readiness, all while continuously optimizing their formation for maximum defensive capability. This concept would require breakthroughs in secure communications that cannot be detected or jammed, potentially using quantum entanglement-based systems currently only in laboratory settings. The strategic implications of the GJX's development extend across multiple domains of future warfare. In the anti-access area denial context, it provides a long-range persistent capability that can operate inside defended airspace, identifying and engaging time-sensitive targets such as mobile missile launchers or command centers. Its endurance allows for patrol patterns that can cover vast ocean areas, functioning as a sensor node in the broader maritime surveillance network. In strategic strike scenarios, the aircraft's combination of payload capacity and stealth creates a new option for conventional precision strikes against deeply buried or hardened targets that would previously have required nuclear weapons for destruction. The program's development methodology itself represents innovation, employing digital engineering techniques that created a complete virtual replica of the aircraft before metal was ever cut. This digital twin continues to evolve alongside the physical aircraft, allowing engineers to test modifications and upgrades in simulation before implementing them on test articles. The manufacturing process incorporates industrial Internet of Things principles, with thousands of sensors embedded in the production equipment monitoring everything from material temperatures during curing to torque values. During assembly, ensuring perfect consistency across airframes. The human infrastructure supporting the program is equally advanced, with training systems for both maintenance crews and mission commanders employing virtual reality simulations that recreate everything from complex maintenance procedures to full-scale combat scenarios. The maintenance concept emphasizes condition-based monitoring rather than scheduled inspections, with the aircraft's integrated health management system continuously assessing the condition of all critical components and predicting maintenance needs before failures occur. As the program progresses toward initial operational capability, it is already influencing broader military doctrine and force structure planning. The People's Liberation Army is developing new operational concepts that integrate the unique capabilities of the GJX with other assets, creating synergistic effects that multiply overall combat power. These include concepts for using the aircraft as a communications relay node between submarines and command centers, as a coordinator for drone swarms, and as a battlefield manager that can direct other assets based on its superior situational awareness. The successful advancement of the GJX program demonstrates a comprehensive mastery of the most challenging aspects of aerospace engineering, from materials science to artificial intelligence, and establishes a foundation for continued leadership in unmanned combat air systems development for decades to come. The technological ecosystem created around this program will inevitably spin off innovations that benefit other sectors of aerospace and defense, while the operational capabilities it provides will fundamentally alter the strategic balance in the Asia-Pacific region and beyond. The continued development of this system represents not merely the fielding of a new weapon, but the advancement of an entire technological paradigm that will define the next generation of aerial warfare.